Understanding how computer memory works and is structured is fundamental to understanding how to program. In this lecture, we will revise how binary numbers work. This knowledge will be critical as we go forward looking at the bitwise operations in this section. As humans have blood running through their veins, computers have electricity. It is the nature of this electricity that is harnessed to store data. Electricity can be in one of two states, off or on. Computers use these states to represent unique data values, where off represents a 0 and on is a 1. You can imagine computer memory to be comprised of many boxes, where each box holds a single light bulb and is therefore capable of storing a 1 or a 0. This smallest size box in memory is called a bit. Because it can hold a value of 0 or 1, it is capable of storing only 2 unique values. 2 bits are capable of storing 4 values, where each value is determined by a different sequence of zeros and ones. When 8 bits are used, a bigger number of 0 and 1 sequences is possible. In fact, 8 bits are capable of storing 256 unique sequences. In computing, 8 bits is called a byte. The sequences of zeros and ones used in computing is called binary. This doesn't mean much to a human, and therefore the binary is usually translated into our own number system. Here's how. First, we consider each box in the sequence to represent a value equal to 2 to the power of something, and working from right to left, allocate each box with increasing power starting at 0. If you would prefer to work with more familiar numbers, you can convert each power into a decimal value, where 2 to the power of 0 is 1, 2 to the power of 1 is 2, and so on. Now let's say we have the binary number 10001100. To convert this to denary, which is a number in our regular counting system, we add together the values of each box with a 1 in it, just like this. There are 1s in the boxes for 128, 8 and 4. Adding these together will give us a result of 140. We can therefore say that 10001100 in binary equals 140 in denary. The largest number you can store in a byte is when all the boxes are filled with 1s. This adds up to 255. Together with 0, it makes up the 256 values that a byte can hold. If the numbers we've been working with look familiar, it's because anything to do with computers will be a power of 2 value. And the reason lies with the electronic nature of the computer and its ability to store 1s and 0s. In this section, we are going to focus on bitwise operations. These manipulate individual bits within a single variable. For bitwise operations, integers are usually used. The size of an integer can be different depending on the programming language you are using. Typically though, it is 4 bytes or 32 bits in length. When an integer is declared to be 0, all the bits are set to 0. But if you know your powers of 2, you can set any of the individual bits in the sequence to a 1. And this is where the real power of bitwise operations come in. So let's take a look at this practically. And we're going to do that in Unity, but we're not actually going to use Unity, just the C# compiler part to print out some values for us. So open up a project in Unity, just empty, 2D, 3D, it doesn't really matter. And what we're going to do is to write a little script to investigate this setting of bits. So down in the assets, what I want you to do is create a new C# script. We're going to call this set bits. Now, in order to run that, we need to have it in the scene. So over in the hierarchy, let's just create an empty object. Let's call it the bit setter, and drag and drop your set bits script onto the bit setter so that it will run when we press play. Alright, so let's now open this up and edit it. So what we're going to do is create an integer, and then we're going to print out what is in that integer. So at the top, let's declare an int b sequence, and we will set that initially to 0. Now we want to print this out to the console, but we want to print it out as a binary value, not as the decimal value. 0. So in your start, we're going to put a debug.log, and we're going to use a C# method called convert.toString, and we give it our integer, so B sequence. And then we have to say what we want it converted to. And in this case, we want it to be converted to base 2, which is binary. So we will actually see the ones and the zeros being printed out. Now, in order to use convert, you'll also need the library at the top. So using system like that, and that will help us out. All right, so once you've got that, let's just save it. And we're going to go back to Unity, press play. The results are going to come up in the console. So let's have a look in our console, and it has printed out a 0, which is what we expect. Now, in this case, it's going to be 0000 for 4 bytes long, but any leading zeros are just going to be left off in this case. So just assume that there's a whole bunch of zeros in front of up to the length of your integer. Right, so how do you think that you would set, let's go back into our code, how would you set the bit on the very end, which is the one on the very right hand side of the sequence, to a 1 with all the others being 0? Well, the first box or the first position in a binary sequence is 2 to the power of 0, which is going to give us a 1 as the result. So if we set B sequence to 1, it will put a 1 in that final column for us. It's got no other choice but to represent the value 1 in decimal, which is what we're working with here, as the binary sequence 0, 0, 0, etc., 1 on the end. Okay, so set that to 1, save it. Let's just go back into Unity, press play, and we will now get a 1, which doesn't sound all that exciting if you see there, because you set it to 1 and you're printing out a 1, but you're actually printing out the binary value 1. So to see it more clearly, let's have a look. Let's go back to the code and think about the 4th box along. So the 4th box along in the sequence, you've got 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. So what is 2 to the power of 3? Well, it's 8. So if we set our integer to 8, then you would expect that we're going to get the binary sequence 0, 0, 0, or the leading zeros, 1, 0, 0, 0. Okay, so let's save this, and we will press play and go to the console, and we can see that binary sequence quite clearly there. Now, here's where the real beauty of these powers of 2 and setting your bit values comes into play. Let's go back to our code. What if you wanted to set your binary sequence to 1, 0, 0, 1, and the rest zeros, of course? Well, you could work out what 1, 0, 0, 1 is, and you could put a 9 in there. Okay, so you could just set equals to 9 and you get 1, 0, 0, 1. But you can also do an addition of the power of 2 values. So 8 plus 1, which obviously is going to be 9, but it's going to give you a 1 in the 1 box, or the first box, and an 8 in the 4th box, because of, you know, the value of the boxes. Okay, so just save this, and let's go and run it and have a look at our little binary sequence, which is going to come up as 1, 0, 0, 1. So now you've set that box, and you've also set that box, knowing which one to set. So what if you wanted to have it add 1, 0, 1, 1? Well, you know the second box is a 2 box. It's the value of 2. So if we go back into our code, we can simply add 2 onto our little sum up here, save it, and then we will press play. In the console, we now have 1, 0, 1, 1 in our bit sequence. Now, you might be looking at this going, well, so what? But you're about to find out in the coming lectures why this is so important and how powerful a concept this is in your game programming, because it's going to allow you to do operations that you would have done quite a long way around before compared to doing it with these bitwise manipulations. So I'll leave this lecture here. You can go on and do a little bit of a quiz testing your knowledge on this, and when we come back in the next lecture, we'll start looking at the magic of bitwise operations.